Welcome to this lesson about line and point symmetry. We will define the concept of line and point symmetry, the symmetrical shapes, and we will see together some relevant examples. If you like this video, please don't forget to subscribe to the channel and to press the bell button in order to receive notifications for the new videos I upload to the channel. Now let's start. Symmetrical shapes. A shape is symmetrical if it can be divided into two parts that are exactly the same, and one part can be folded around the line to fall exactly on the other half. So let's take the heart example we see here. Now imagine this heart as a piece of paper. Now we draw on this heart this line here that we believe to be in the middle, and we try to fold the heart, which is now a piece of paper, around this line in the middle. By doing that, we notice that the first half of the heart, which is this one, will fall exactly on the other one. And we conclude from this that those two parts are exactly the same, or in other words, are identical, and they have the same area, the same circumference. So we say that this heart shape is symmetrical. Same applies to the butterfly shape we see here. And now if we take the third example, which is the green square we see here, we notice that this square can be split into two identical shapes using more than one line, or by more than one method. And for example, using this line we see here, we can see that this square is divided into two parts. This is one of them, and this is the other one, which are exactly the same. And this line also, the diameter splits the square into two identical parts. The first one is this triangle we see here, and the second one is this triangle. And if we try and fold this triangle around the line, it will fall exactly on the below triangle. And so they are also two identical parts. So the number of methods or the number of lines we can use in order to split this square into two identical parts are 4 in this case. However, if we move to the other row of examples, we can simply see by taking this heart that the first part here is not identical to the second part. And so if we tried and folded this first part around the line in the middle, it will not fall exactly on the other part. And there is no other way. There is no other way by which we can split this shape into two identical parts. So we say that this shape is asymmetrical. Same applies for the butterfly shape. We notice that here we removed a small part of the wing that existed before here. So this wing is no longer identical to the other wing here on the right, and we cannot fold this right part around the line in the middle to fall exactly on the left part because of that. And so the left and the right part are not identical. And same applies here after we remove this piece from the above square. So there is no way also we can split this square into two identical shapes. So we call these three shapes asymmetrical. So now we define the concept of line of symmetry, and actually we have already spoken about it in the previous slide, but we will emphasize the concept further. It's the line that splits the shape into two parts that are exactly the same, and one part can be folded around the line to fall exactly on the other part. So here we have a couple of geometrical shapes, and we can see the lines of symmetry in each one with the number of possible lines of symmetry. So we have already seen the square example where it has 4 lines of symmetry. Here the rectangle has 2 lines of symmetry, because if we thought of drawing the diameter here, for example, those will be equal. However, if we cannot turn, let's say, this triangle around this diameter to fall exactly on this other triangle we see here. So this is not considered a line of symmetry. Same applies for this one we see here. So the rectangle has only 2 lines of symmetry. In the case of the equilateral triangle, we have 3 lines of symmetry, because we know that in the equilateral triangle, each of these lines of symmetry splits the triangle into 2 parts that are identical. So this angle equals this one equals that one, and those are the same if we are talking about this line, for example. So we can, if we try to fold this triangle around the line in the middle, it will cover exactly the left triangle. So the equilateral triangle is symmetrical, and it has 3 lines of symmetry. This is the first one, and we have the second, and we have the third. Similarly, we can see that the hexagon, for example, has 6 lines of symmetry. So the first one we can see is this one, and it splits the hexagon into 2 identical parts. The first one is that one, and the second one is that one. We have also this one. Similarly, it splits the hexagon into 2 identical parts, and we can continue with them. Sorry. So we notice that their number is 1, 2, 3, 4, 5, and 6. Then this is the same one we got here first. In the case of the circle, we have an infinite number of lines of symmetry. Why? Because each line of symmetry here is a diameter, and it splits the circle into identical halves. And since we have an infinite number of diameters in the circle, so it means we have an infinite number of lines of symmetry. So let's now talk about the point of symmetry. 2 shapes are symmetrical with respect to a certain point if every point from the first shape is matched to a point from the other shape that falls the same distance from the point of symmetry, but in the opposite direction. So to clarify this further, let's consider this shape here of two butterflies. We notice that if we take a random point from this butterfly we see here, and let it be this point, and if we draw a line that connects this point with a point of with the point that is supposed to be the point of symmetry, then we extend it with the same length, we notice that we reach a point from the other shape that matches the first point. However, it's located on the opposite direction of the supposed point of symmetry. Now, let's take another example. This point, for example, we connect it to the supposed point of symmetry with, we notice that here there is a small line that connects those 2 points, and we extend it with the same length, and we reach another point on the other shape that is matching with the first point we started from. Now, this works if we take any random point. We will be able to find a point on the other shape that falls the same distance from the point of symmetry, but in the opposite direction of the first point. However, if we take another example, let it be this point here. And we take this point on the butterfly and we connect it to this point, and we try to extend it with the same length. We notice that we don't reach a point here on the other shape that is matching to the first point we started from. This means that this new point is not a point of symmetry. Now, it's good to mention that this rotation, point symmetry is identical to the rotation symmetry of order 2, where the order is defined as how many times the shape matches the original as we perform one full round. So here, if we imagine we have 2 plastic butterflies connected with a stick to this point, where this point falls in the middle of the stick, and we try to grab this butterfly and we turn it 100 degrees around the point. So you can imagine it moving this way. Then after 180 degrees, it will fall exactly on the butterfly here. At the same time, as we do this 180 degrees rotation, this butterfly itself will fall on the first butterfly. So this is the first time the shape matches itself by rotation. Now, in order for the first butterfly to return to its original position, because as we said, now it falls here, this butterfly here, after the first rotation, it falls here. So we need to return it back to its original rotation. So we go 180 degrees again. So it will fall back on its position. And here we completed one full round in order to return to the first state of the shape. And we call this the rotation symmetry of order 2. Here we are giving examples of rotation of order 3 and of order 6. In the case of rotation of order 3, we notice that if we have this part and that one and this one, we notice if we started the rotation from part X here, then after one round, X will be here. After 2 rounds, it will be here. And then after 3 rounds, it will return back to its first position. So we call this rotation symmetry of order 3. And here same, but it's a rotation symmetry of order 6. Now let's take a test. Find a shape that is symmetrical to the below shape with respect to the red line and to the point O. So here we want to find the shape that is symmetrical to this shape with respect to this line. What we need to do is to take the points from here that fall on the edges of the straight lines and to find the points that are symmetrical to these points with respect to the line. For example, let's take this point. I draw a vertical distance here and I extend it with the same length. So I find this point which is symmetrical to this point with respect to the red line. Now I take another point, which is that one. I extend it vertically. I draw a vertical column that is perpendicular to the red line I see here, and I extend it vertically. I reach this point, then I draw a line that connects between the two. So this line is symmetrical to that one. I continue same way. So I take this point here, 1, 2, and I extend 1, 2. Then I draw a line here. Same for here. 1, 2, 1, 2. Then I draw a line such. Now I take this point, count 3, 1, 2, 3. Here 1, 2, 3. And finally I take this point. Again 1, 2, 3. 1, 2, 3. And I forgot to connect between these 2 points. So that's it. And then same way, I try to find here. I count, I take this point, 1, 2, it falls here, take this one. I connect, take that one, 1, 2, connect, then I take this one. One, two, three. And then finally I have number 1. So I take this point, I take that point. It's kind of close, it's not exactly accurate. And I take this point. Oh, it falls here. So this is the shape that is symmetrical to the original shape with respect to the red line. Now we will need to find the shape that is symmetrical to this shape here with respect to the point O. For this, we need to take every point from the edges and connect it to the point O and extend it with the same length. So let's start, for example, by number 5. We see here. So we take this point at first. We connect it to point O, like that, and we extend with similar distance. Of course, you can use a ruler in order to make sure the distances are matched correctly, but here anyway, I have a math canvas, and this will help me in measuring the right distances. So here it falls. Then I take this point we have here. So I connect it to this point and it will fall here. Okay, I connect between the 2 points. Now I take another point here, 1, 2, then it will fall here. And now this point, 1, 2, and 2, it falls here, and I connect them. And then I take that one. It will fall here. Finally, this one. So this is the shape that is symmetrical to this shape with respect to O. Now let's take number 3. So first I take this point, I extend it with the same length to here. Then that one, I connect them. Take now this point. When I have to extend it vertically, it's the easiest. I connect them. Then I take this point. Okay, then that one. Count 1, 2, 3, 1, 2, 3. Okay, then the last one, this one. So I connect it like that. It will fall here. This is the shape that is symmetrical to number 3 here. Now the last one is number 1. I take this point, I extend it, I extend it again, it will fall here. Then I take this point, it will fall somewhere here. And finally, I take that one. It will fall here. I connect. So this is the shape that is symmetrical to that shape with respect to point O, which is now the point of symmetry. And here we reach the end of the video. Thank you for watching.